Welcome to Multivariate Calculus. Today we are going to explore one of the most powerful tools in mathematics, the multivariate chain rule. If you have ever wondered how to track changes in a system where everything depends on everything else, you are in the right place. We will build this concept from the ground up, so do not worry if it sounds complex right now. Let us dive in and see how it works. To understand why we need this rule, imagine you are hiking up a rugged mountain. Your altitude depends on your exact map coordinates, which are your east and west or north and south positions. But your position depends entirely on how long you have been walking. So your altitude ultimately depends on time. If you want to know how fast your altitude is changing at any given second, you cannot just look at the map. You must combine how the mountain slopes at your location with how fast you are walking in each direction. This linking of dependencies is exactly what the multivariate chain rule does. Now that we understand the hiking analogy, let us look at the mathematical foundation. To understand where the chain rule comes from, we start with the total differential. This formula represents the tiny overall change in a function when all of its input variables change by a microscopic amount. The symbol dz represents the total microscopic change in the output. The partial derivative of z with respect to x measures how much the output changes when only the first input changes, keeping everything else frozen. The term dx is the tiny change in that first input. The second half does the exact same thing for the second input. As these individual changes increase, the total change increases as well. Building on the total differential, what happens if both inputs are changing as time passes? We simply divide the entire previous equation by a tiny change in time, dt. This gives us the standard chain rule formula for one independent variable. The term dz over dt is the total derivative, meaning the overall rate at which the final output changes as time moves forward. The term dx over dt is the ordinary rate of change of the first intermediate variable with respect to time. The formula clearly shows that the total rate of change is a weighted sum. If the partial derivatives increase, meaning the surface gets steeper, the total rate of change will also increase. Before we apply this formula, let us look at a visual trick to help you remember it. You are looking at a chain rule tree diagram. At the very top, we have our main output variable z. From z, the tree branches down to the intermediate variables x and y. Finally, both x and y branch down to the single independent variable at the bottom, time t. Along each branch, we write the derivative of the top node with respect to the bottom node. To get the final formula, you simply multiply the derivatives along a single path from top to bottom and then add the results of all the different paths together. Now that we have our formula and visual tree, let us apply this to a specific mathematical problem. We are given a main function z equals x squared times y. The intermediate variables are x equals sine of t and y equals e to the power of t. We want to find the total rate of change of the output with respect to time, exactly at the moment when time is 0. Our strategy is to compute each piece separately. We start by taking the partial derivative of the main function with respect to the first input, x, treating y as a constant, which gives 2xy. Then we find the partial derivative with respect to y, treating x as a constant, giving x squared. With the partial derivatives found, we move on to the intermediate variables. We need to find their ordinary derivatives with respect to time. For the first intermediate variable, x equals sine of t, the derivative with respect to time is a standard trigonometric result, giving us cosine of t. We do the exact same thing for the second intermediate variable, y equals e to the power of t. The derivative of the natural exponential function is a unique case in calculus, as it is exactly equal to the original function itself, so it remains e to the power of t. We now have all 4 necessary mathematical pieces to assemble our chain rule. Having gathered all our pieces, we substitute these expressions back into our main chain rule formula. We multiply the partial derivative with respect to x by the time derivative of x and add it to the product of the y derivatives. This gives us a long algebraic expression. However, the problem asks for the rate of change at a very specific moment when time is 0. Before we can plug this time value into our final equation, we must figure out what the intermediate variables are at that exact moment. Substituting 0 into their equations, we find that x equals sine of 0, which is 0, and y equals e to the power of 0, which is 1. Now we substitute all of our known numerical values into the assembled chain rule equation. Every variable is carefully replaced by its value at the specific moment we are analyzing. This step removes all the algebra from our expression and turns our complex equation into a simple arithmetic problem. Because the first input x was 0 at this specific moment, both terms in our addition problem become 0. We add 0 to get a final result of 0. This final result tells us physically that at the exact moment when time begins, the overall output of the function is momentarily stationary, neither increasing nor decreasing. We have successfully solved a problem with one independent variable, but the chain rule becomes even more powerful when the intermediate variables depend on more than one independent variable. Imagine baking a pizza in an oven. The final taste depends on the temperature and the baking time. However, the temperature and the baking time might both depend on two other factors: the specific oven setting you choose and the thickness of the dough. In this scenario, we have two intermediate variables and two independent variables. We must use a slightly expanded version of the chain rule to find how the final output changes when we adjust just one of those independent variables. To handle this new scenario, let us look at the expanded formula. This formula calculates the partial rate of change of the final output with respect to the first independent variable, which we will call u. Notice that we are now using the partial derivative symbol everywhere because the intermediate variables depend on multiple things, not just one. The term partial z over partial u represents how much the final output changes when we tweak only the first independent variable. We still calculate this by tracing every possible path through the intermediate variables, multiplying the partial changes along each path, and adding them up. If the intermediate dependencies grow stronger, this overall partial derivative will also increase. Let us look at a problem involving multiple independent variables using our new formula. Suppose our main function is z equals 3x minus 2y. The intermediate variables are defined as x equals u plus v and y equals u minus v. We need to find the partial derivative of the main function with respect to the first independent variable, u. The strategy remains exactly the same as before, but we must be careful to use partial derivatives for every step. We begin by finding the partial derivative of the main function with respect to x, which is simply 3. Then the partial derivative with respect to y gives us negative 2. Continuing with our strategy, we now look at the intermediate variables. We need to take their partial derivatives with respect to the first independent variable, u. For the first equation, x equals u plus v, we treat v as a constant, so it vanishes. The derivative of u with respect to itself is just 1. We repeat this exact process for the second intermediate variable's equation, y equals u minus v. Again, we take its partial derivative with respect to u. The second independent variable v is treated as a constant and disappears, leaving us with a simple derivative of 1. We now have all the components ready to combine. We have successfully gathered all the necessary components, so let us put them together. We substitute these 4 numerical values back into the expanded chain rule equation. We multiply the corresponding parts for each path through the variables, multiplying 3 by 1 and negative 2 by 1. Finally, we set up the addition to combine the paths. We perform the basic arithmetic to find our final answer, subtracting 2 from 3. The result is a positive constant number of 1. This physically means that for every single unit we increase the first independent variable, u, the final output of the main function will increase by exactly 1 unit. Now that you know how to calculate these rates of change, you might wonder where this is actually used. The multivariate chain rule is an absolutely essential tool in almost every branch of modern science and engineering. In thermodynamics, for example, the pressure of a gas depends on its volume and temperature, both of which might be changing over time as a piston moves. Without the chain rule, engineers could not calculate how fast the pressure inside an engine is building up. In the field of artificial intelligence, the chain rule is the mathematical engine behind backpropagation. By tracing errors backward through multiple layers of intermediate variables, it tells the computer exactly how to adjust its internal settings to learn from data. We have covered a lot of ground today, so let us review the key takeaways. The chain rule for functions of several variables is simply a method for tracking how changes cascade through a system with multiple interconnected parts. By breaking a complex dependency into smaller, direct relationships, we can calculate the total rate of change systematically. Remember the core rule. You just find the rate of change along every possible path from the input to the output and then add all those path contributions together. Mastering this rule allows you to analyze dynamic, real-world systems where many different factors are changing all at once. You now have the tools to handle complex multivariate dependencies.